Hello and welcome. In this video, we're going to take a look at another application of the definite integral, but we're going to add an extra dimension to it. Rather than thinking about area, we're going to take a look at volumes in this case. Now, we're not going to dive into multivariable calculus, which is maybe how you'd find the volume of a lot of different kinds of shapes. But we can stick with single variable calculus and find volumes that are obtained by taking a region and revolving it around an axis. The axis could be horizontal or it could be vertical. In fact, we can take a look at both of these in this video. But thinking about how we obtain this, well, think about when we're revolving it around, we're going to get something that's sort of like a circle. Cross sections are going to be circular in some form. So let's start off with a classic example of something that has cross sections that are always perfect circles. Let's start off with a right circular cylinder. We already know how to calculate the volume. We've got the formula pi r squared h possibly just memorized. Now, we might want to think about where that comes from. Well, one way to think about the volume of this object would be to add up areas of cross sections from one end to the other. The area of each cross section is simply a circle. Now, if the axis is parallel to the x-axis, then we could think about adding things up from a position x equals 0 to a position x equals h. So along the x-axis, we'll be taking little slices at various different places for x. Now, in this case, every cross-section is the exact same surface area, pi r squared. But thinking about other objects, for example, a cone, as we move from one position along the x-axis to another and take a look at slices of this volume of revolution, those surface areas are not always going to be the same. Our first is going to be very small at one end of the cone, and as we move towards the opposite end of the cone, the slices have much larger cross-sectional area. So it might be useful to think about the cross-sectional area as being a function. Let's say that this area is equal to A. Well, A is going to depend on where we slice this cylinder. So let's suppose we slice it at a place x star, where x is a value between 0 and h. All right, this is starting to sound a little bit more like a Riemann sum. Well, let's make these very, very thin slices. Let's say the width of every one of these slices is delta x. All right, what we have here is a very thin disk, really. It's a circular cylinder on its own. It's so thin, though, that delta x is nearly 0, as long as we take several slices. The volume of this disk is simply taking the cross-sectional surface area, A at x star, multiplied by delta x, and we can get the volume of the entire circular cylinder by adding up all of those little mini volumes. And then this can apply to any shape in general, including the cone. Just thinking about A of x star as being a function, then the areas will change from one end of the cone to the other, and we can add them all together and get the volume of the entire cone that way. Now, much like with Riemann sums, this is just an approximation. You can see here with this jagged edge, these disks are never going to be perfectly the shape of this cone. But what if we take the limit as n goes to infinity? Well, then there we go. We get the volume is just the definite integral from a to b of this cross-sectional area function. And this cross-sectional area function, a of x, is simply just pi times a radius at each x star squared. So really, in order to calculate volumes of revolution, we need to be able to find some way to determine the radius as a function of x. And then we can just simply have this volume formula, pi times the definite integral of r of x squared from x equals a to b. In the circular cylinder, that was from 0 to h, and the radius would always be a fixed constant. And if you integrate pi times the definite integral from 0 to h of some constant r squared, you should end up getting pi r squared h. Well, let's try finding the volume of that cone. You might remember the formula for the volume of a cone, but let's actually try to prove it ourselves. Let's see if we can find the general formula for the volume of a right circular cone with a radius of r and a height of h. I'm just using capital R and capital H here, just to hopefully not confuse us with what we are thinking about as the radius of every cross section. Now, when I draw a cone, I like to usually draw them so that the flat base is resting on the table and the pointy part is pointing upwards. But that's not the only way to draw a cone. We could just as easily have the right circular cone. We could just as easily have the axis of revolution be horizontal. Now we can maybe think about either one of these scenarios, but we should get the same value no matter what we choose. So in the left example, we have a vertical axis of revolution. And in the right picture, we have a horizontal axis of revolution. So to make things easy, let's put those axes exactly on the y and x axis. Now we'll have to set these up quite differently depending on which orientation our axis is. Let's start off with the x-axis and take a look back at the y-axis in a moment. Let's set up this cone so that our y-axis is at the one pointed end of the cone. And so what we're really thinking about is taking a region and revolving it around, and that region in this case is this triangle. And with that triangle shaded in, we can think about little cross sections as being circles. All right, well, now we've got one of these cross-sectional circles. Now this thin slice has almost no thickness, but you can still think about it as being a thin disk. The delta x here is the thickness of that disk, so we know that our integral is going to be set up so that we have dx at the end of it. All right, then our interval for x is simply going to be the boundaries along the x-axis for this triangle. Since we've got one end of the cone of the origin, then our interval for x is going to be simply from 0 to capital H. So we've got that part figured out already. Now we need to figure out the radius of this cross section. Let's label that little r. Little r here will vary depending on where we are looking at each of these disks. R is going to be all the way from 0 up to capital R. But what we really need here is r to be a function of x. Well, r of x is just simply the distance from 0 to this diagonal line. And this is a function. We can see that it has a y-intercept of 0 and rise up a run of capital R over capital H. So this function is simply y equals rise over run times x. And r of x is simply the distance from 0 to y. So it's pretty easy to give an expression for r of x. There's our radius. Okay, now we're ready to set up this definite integral. So we're going to integrate over the interval from 0 to h. And then the function that we're integrating is not just the radius. We're integrating pi r squared. That pi can come out front. And r of x squared, and r squared is r over h times x all squared. And remember, the width of each of these little disks is dx. So this is going to get our volume. Now, r and h are simply just constants in this problem. So when they are squared, they're going to be brought out front of this integral. And then we're simply going to integrate x squared from 0 to h. So the antiderivative x cubed over 3. And when we plug in h, we're going to get 1/3 h cubed. When we plug in 0, we're going to get 0. And that gives us our volume equation. That h cubed will cancel with h squared to give simply just h. And the volume of this cone is 1/3 pi r squared h. Okay, well, going back to a vertical axis, we should get the same result. But we have to set this up a little differently. This time around, our axis of rotation is along the y-axis. So if we want to make small slices that are circular and get disks, then the thickness of each disk in this case is going to be a slight change along the y-axis, or delta y. And so here's a typical cross section at some place, let's say y star. Okay, well, here's that radius. And we can see that that radius is not always going to be the same depending on where we slice this along the y-axis. So we're going to let radius be a function of y. And to illustrate that delta y, you can still think of this as having a very small thickness, but this time delta y. All right, so let's think about how we can set this up to get an interval for y. It might make a lot of sense here to have our x-axis be at the base. Okay, well, here's our x-axis, and we can see that this radius is always just going to go from x equals 0, which is the y-axis, to this diagonal line on the right. And you can see that really we're just revolving this triangular region around the y-axis. Okay, well, now that I've got this set up, I can see that my interval for y goes from y equals 0 up to y equals h. So that part is pretty similar to how we set up the interval when we were revolving around the x-axis. What's a little bit different is here. We need to find an expression for this diagonal line in terms of y now. So we see that this is going to have a negative slope. It has got a rise of negative h and a run of r. So we can say that this function is y equals negative h over r times x. But what we really need is to have x in terms of y. So that means that our radius, r of y, since it's going from x equals 0 to x equals negative r over h times y, is simply going to be the distance negative r over h times y. All right, setting up volume roughly the same way, we are going to be integrating from 0 to h of pi r squared, where r is a function of y, and integrating with respect to y because the thickness of each disk is going to be dy. Now the pi can be put out front as a constant again. Now take a look, since this is being squared, you can see how that negative sign doesn't really matter. That negative sign is canceled out, and we see that we end up with the same calculation as before, but just with a different variable. And because the value of a definite integral doesn't depend on what we use as the variable itself, we should end up with the same result. So now you can see, this is how we get the volume of a revolution, depending on whether we are revolving around x or y. If we're using a horizontal axis, then we should maybe see if the radius can be written as a function of x. If we were revolving around a vertical axis, then we should see if we can get the radius as a function of y. Now, in a previous video, we looked at finding the area of a region between two curves. Now, what if we were to take that region and revolve it around a central axis? Then it's conceivable that when we take that region and revolve it around, we could end up with a volume that has a core that is hollow, which makes it kind of an interesting calculation, but not that much more difficult. Instead of having thin slices looking like disks in that case, it would still be circular, but since it's got a hollow core, we could think of that as being more like a washer shape. So let's take a look at a couple examples like that. In the washer's method, we're looking at a region bounded by two functions over an interval. So here I've got an interval, let's say from a to b, and x equals a actually gives us an intersection point, but let's say just this line here is the vertical line x equals b. And we're going to take the region bounded by y equals f of x, y equals g of x, and x equals b, and revolve that. Let's start with around the x-axis. I'll draw a purple line here along the x-axis. That's our axis of revolution. And in order to get an idea of what the solid would look like, let's just take a mirror image of what's above the x-axis, reflect it to below the x-axis. With this reflection, we might be getting an idea of what a cross-section will look like. At some arbitrary value, xi star, we want to think about a disk at that point in time. Well, now it's a disk with a hole in it, and that's why we're going to call it a washer method. There's going to be a hole with an inner radius. You can see that hole represented by this little circle, and then we're going to have an outer radius forming the outside of this washer. Well, this now means that we have two radiuses to worry about. An inner radius that goes from the axis of revolution to our y equals g of x, and an outer radius that goes from our axis of revolution all the way to y equals f of x. So when we're thinking about the washer's method, we have r outer and r inner, two different radiuses. And the cross-sectional area, this green region, is simply just the area of the outer circle minus the area of the inner circle. Pi times r outer squared minus pi times r inner squared. We can factor a pi out of that, and we'll end up with our definite integral. Well, because our outer radius is f of x and our inner radius would be g of x, this will give us our integral of f of x squared minus g of x squared integrated from x equals a to x equals b. Now, what if I were to take that axis of revolution and I were to sort of shift it vertically? If I were to take that axis and shift it down by 1 unit, then that's going to affect the mirror image. The mirror image is now going to be even lower, and you can see that reflected here. Any point that is 4 units above the axis of rotation is reflected and rotated 180 degrees down to this point 4 units below the axis of revolution. So let's just make a quick adjustment. We don't have to rethink everything, but we just need to think about inner radius and outer radius. inner radius is going to go from this horizontal line, which is y equals -1 now, up to y equals g of x. Well, that's just simply one more unit than it used to be earlier. So that inner radius is going to be g of x plus 1. And our outer radius is going to be from the axis of revolution to y equals f of x. That's going from the line y equals -1 all the way up to the red line. That's just simply one unit more than it used to be. So that's just going to be a small adjustment to what we define as the inner and outer radiuses. Inner radius is g of x plus 1. Outer radius is f of x plus 1. But the form of this volume by Washer's method is still the same. All right, well, last but not least, what if we were to maybe move this axis of revolution upward several units? All right, well, this is definitely going to adjust things a fair bit, but the principle is still going to be the same. Let's suppose that we just move this horizontal axis to the line y equals a. All right, then revolving around that, then we will look at our inner radius as being the distance from a measured downward. That distance would be a minus f of x. Now we can take a look at our outer radius. That's also going to be measured downwards from y equals a down to y equals g of x. So that distance is going to be a minus g of x. But you can still see here that our integral is set up the same sort of way. Pi just always will be there because we're taking pi r squared as being cross-sectional areas. But we have outer radius squared minus inner radius squared. And here that a comes from the fact that we've now moved this to an arbitrary axis y equals a. Now the process by which we do washers around a vertical axis is very similar. With the vertical axis, we can put that at any value we like. X equals b would just be an arbitrary vertical axis. We just need to measure our inner and outer radiuses to be from that vertical axis. And then pi times the integral from some sort of y equals c to y equals d, and we have our outer radius squared minus inner radius squared. Well, let's try an example of finding a volume of revolution using washers. All right, well, let's see if we can find the volume of the solid obtained by revolving the region bounded by the curves y equals x squared, our classic parabola, and y equals x, just a simple diagonal line. But let's make sure to make this a little bit tricky by revolving around the line y equals 2. Let's see what kind of a solid object we get. Now, it's not too hard to draw these two shapes. It's not hard to find where they intersect. So let's try making a little sketch here. All right. Well, it's pretty easy to find the two intersection points, 0, 0, and 1, 1. Now, when we want to try to revolve this around the line y equals 2, we might want to take a look at the reflection on the opposite side to get an idea of what a typical washer looks like. There's our reflection. Now, you can see that when we try to form a solid by revolving this around the horizontal axis, we're going to end up with a hollow core. You can see here I've drawn 3 circles, and that's going to be our hollow core. And that's going to be our inner radius. So if we want to draw that radius, it's going to be measured from y equals 2 down to y equals x. So for our inner radius at any point x, we would have 2 minus the red function x. Now, for our outer radius is measured from y equals 2 down to the blue function y equals x squared. So that distance is going to be 2 minus x squared. And the cross-sectional area of each of these washers is simply going to be pi times r outer squared minus r inner squared. And we are going to be integrating from x equals 0 to x equals 1. And that's coming from the two intersection points of y equal x squared and y equal x. So our volume, integrating from 0 to 1, of pi times r outer squared minus r inner squared. And to evaluate this definite integral, we should just expand this out, collect like terms, and then use some power rules. And this is going to give us a volume of 8 pi over 15. Now my sketches here are far from perfect. They're not going to get you necessarily an intuitive understanding of what's going on. But don't worry, I've got another backup tool here to kind of improve upon the visualization aspect of this, and that's using Maple. So let's take a look and see. There's a lot of built-in commands or commands that you can take a look through to be able to visualize these volumes of revolution. Okay, here I've got a nice worksheet with a few commands included at the beginning to include some extra plotting tools and some additional commands that are very specific for volumes of revolution. Now I'm just going to run the first few of these here, and you can see I've got my top function being y equals x and my bottom function just being x squared over the interval from 0 to 1. So I'm just assigning those as nice, easy to use top, bottom, and interval. All right, so the volume of revolution command here, and you can see distance from axis is equal to 2. By default, we have a horizontal axis, and it's usually at the x-axis. But we're going to shift that up by 2 to give us our axis of revolution of y equals 2. So here's what that region looks like. Take a look. You can see, well, it's this very thin sliver here, the area between y equals x and y equals x squared is this really dark shaded area here where my mouse cursor is. That is being rotated around, and you can see we have a hollow core. In fact, more or less just a giant shell. It kind of looks like it could be the nozzle for some sort of rocket. Okay, well, we've got the general idea of what that shape might look like now. And you can see the axis at y equals 2. We've got the x-axis here, and, well, I guess we're going to be throwing in an extra axis there to kind of represent volume. So this would be like a z-axis. Now, what about this idea of taking thin disks? It's kind of hard to see from this picture. So I've included a couple other volume of revolution commands with lots of options, and I'm going to display them both at the same time. And with this, I've removed the solid, and you can just see that I've got a washer. It's this thin little disk here, but it's got a hole in it, so it's more or less a washer. Now, I am deciding to use 20 washers to get from x equals 0 to x equals 1. So each of them is going to be a tiny little rectangle, and then rotated around y equals 2. This is the first of those washers. And as I shift over a little bit more, my next frame here, my second washer, third washer, and somewhere in the middle you can start to see how the radius of the inside and the radius of the outside are changing every time I go to the next washer. And I can make this into a consistent animation so we can just watch all of these washers add together to get the solid. So you can see as I rotate this around, the inner radius and outer radius are varying as I pick a value along the x-axis from 0 to 1. So inner and outer radiuses here are a function of x. Now, like I say, these are very similar washer type of scenarios that you can run into if your axis is vertical. We can simply take this axis and start shifting it this way. And we can imagine that this is now going to be our x-axis and y-axis. Very, very similar. And now the washers are going to be going up the y-axis. But you're still going to be having your inner and outer radius. We'll have our outer radius squared minus our inner radius squared. But it's very much the same kind of process. There you go. I hope that kind of gives you a little bit of an idea of how we can obtain the volume of a region rotated around an axis. Now, as it turns out, and unfortunately this is the bad news, is that sometimes these integrals are not going to be very easy to solve. Sometimes your inner and outer radiuses, when they're given in terms of x, and then you're integrating along the x-axis, might be very difficult. There's an alternative method to finding volumes as well, where we can use sort of like a rectangle going horizontal and rotated around a horizontal axis. Instead of inner and outer radius, we end up with this sort of left and right boundary of a shell being rotated around. That's a little different method than using washers. We'll have to save that for a future video, but this should kind of get you covered and sort of into the idea of thinking about volume in terms of integrals. Thanks for watching, and I'll see you in the next video.